So, welcome to this class on hardware security. So, today we shall be talking about different topic. We will be talking about a finite field architecture, like last class we discussed about multipliers. In today's class, we will discuss about another important class of arithmetic circuits in finite fields, which are called as finite field inverse. So, how to compute finite field inversions. So, more specifically, we shall be talking about multiplicative inverse in GF 2 to the power of m, which is a characteristic 2 field. We shall be talking about the Ito-Tsuji inversion algorithm. We shall be talking about a generalization of the Ito-Tsuji inversion algorithm, and time permitting we shall be discussing about hardware design and also performance of the corresponding hardware circuit. So, to start with, how do we compute a multiplicative inverse, or what is the definition of a multiplicative inverse? So, multiplicative inverse means that given an element A, we wanted to find out its inverse, which is denoted as A inverse or A to the power of minus 1 in the field, such that if I multiply A with A inverse, I get the unit, or I get the unity element in the field, or I get 1. So, to start, so like there are different techniques for finite field inversion computations. The most important ones I have kind of written here, like the first one is the extended Euclidean algorithm, which is a more generalization of the Euclidean algorithm, which is used to compute the greatest common divisor of two numbers. There is another algorithm, or there is another result, which is very famously known as the Fermat's-Little theorem, which also can be used to compute multiplicative inversions. So, so the comment here is that the Fermat's-Little theorem is more efficient on hardware than the Euclidean technique, because the Euclidean technique, as you probably know, is that it will be resulting in a computation which requires more intensive operations, and also essentially will require more number of clock cycles. So, essentially, right, we resort to Fermat's-Little theorem, and just to state how a Fermat's-Little theorem works. So, when we want to compute A to the power of minus 1, the idea is that, and I want to do a modulo of the field, then, or modulo of the total size of the field, then what we do is we try to compute A to the power of minus 1 as A to the power of n minus 2 modulo n. Note here that the definition of n is such that n can be any number as such, but A has to be co-prime with n. Okay, that means the greatest common divisor of A and n has to be 1, or in another sense we can also say this as A belongs to the multiplicative group which is created by n, which is denoted often as Zn star. Okay, so, you can also say for simplicity that let us choose n as a prime number, in which case all the elements which are non-zero, like starting from 1 to n minus 1, belong to its multiplicative group. So, just to take a small example, so suppose I take n equal to 5, which is a prime number. So, then you can easily see that 3 to the power of 5 minus 2 modulo 5 should be its inverse. You can check it that this turns out to be 2, and therefore, if I multiply 3 with 2, then I get 6, which modulo 5 is 1. Okay. So, therefore, 2 is indeed the multiplicative inverse of 3 modulo 5. So, just to generalize this, the generalization is based upon a particular parameter or particular function, which is called as the Euler's Totient function, often denoted as phi of m. Okay. So, suppose that A and m are integers, such that the greatest common divisor of A and m is 1, that means A and m are mutually co-prime or relatively prime. Then the number of integers in Zm that are relatively prime to m and does not exceed m is often denoted as phi m. Okay. And this is called also as the Euler's Totient function or the phi function. Okay. So, just to define, right, the phi of 1 is taken as 1, this is initialize the phi function. Okay. And subsequently, right, if I for example want to compute 26, m equal to 26, and I want to calculate phi of 26, then it turns out to be 12. That means, there are 12 numbers which are co-prime with 26. If p is prime, then it is natural to understand that phi of p will be p minus 1. Okay. Just as we saw in the example. And if n is equal to, like, so here I have just tried to kind of tabulate the values of phi n. So, you will see that phi n is a pretty much irregular function. Okay. It is neither monotonically increasing nor monotonically decreasing, it is kind of an erratic function, but luckily, like if you know the prime factors of n, then you can compute phi n quite efficiently. Okay. However, I am not going into that definition here, but rather we will take a look into Fermat's-Little theorem, which is stated here using the phi function. Okay. So, for example, if I take the greatest common divisor of a and m as 1, okay, and then I can write a to the power of phi m is congruent to 1 modulo m. This equation is also called as the Euler's function or Euler's theorem. Okay. Fermat's little theorem is actually a special case of Euler's theorem, where m is a p, which is a prime number. Okay. And if it is a prime number, then I can write phi of p as p minus 1. So, what we get is a to the power of p minus 1 is congruent to 1 modulo p. If you have the field which is gf 2 to the power of m, therefore, right, where there are 2 to the power of m elements in the field. So, this is the extension field that we saw in the last class, okay, where you extend from gf 2 to gf 2 to the power of m using an irreducible polynomial whose dimension is or degree is m. Okay. So, then we know that a to the power of 2 to the power of m minus 1 should be congruent to 1, which means that if I want to compute a to the power of minus 1, then I need to compute a to the power of 2 to the power of m minus 2, okay, because essentially that should be giving me the multiplicative inverse. Okay. So, therefore, right, how will I compute this a to the power of 2 to the power of m minus 2 is what we need to discuss if I want to compute a to the power of minus 1 or the multiplicative inverse of a. So, here there is a technique which is basically based on what is called as an addition chain. Okay. So, if I want to naively compute a to the power of 2 to the power of m minus 2, then you can see that I will require m minus 1 squarings and m minus 2 field multiplications. Okay. Now, multiplication is costly. So, we do not apply this naive method. Instead, we essentially can apply an algorithm which is called as the Ito-Suji inversion algorithm, which uses the addition chain. Okay. So, let us define an addition chain. How or what is the definition of addition chain? So, addition chain for a positive integer n is a sequence of n of a sequence of natural numbers, okay, starting from u0, u1 and so on to say ul. That means, I will say that L is the length of the addition chain, such that I will initialize u0 to 1 and ul to n. That means, since it is the addition chain for n, the starting point is 1 and the end point is n. Okay. The in between values we need to determine. Okay. But there is a restriction. The restriction is that any sequence in this addition chain should be obtained by the sum of previous two numbers. Okay. That means, for example, if there is ul or say ui, then ui should be essentially expressible as a sum of uj plus uk. That means, should be expressed as a sum of the previous two numbers, okay, and such that uj and uk both belongs to this addition chain. Okay. So, therefore, I should be able to express like ui as the sum of uj plus uk. Okay. So, for example, right, if I want to compute, say, for example, you can see in this addition chain that this is an addition chain for 162. So, I have started with 1, my end point is 162. You can observe that in this addition chain 2 can be obtained by adding 1 with itself. Okay. Likewise, 4 can be obtained by adding 2 with itself. Likewise, 5 can be obtained by adding 4 with 1. Okay. 10 can be obtained with 5 with 5, 20 with 10 with 10, 40 with 20 with 20, 80 with 40 with 40, 81 with 80 and 1, and 162 where we add 81 with 81. Okay. So, this kind of addition chain where one of the numbers is the previous number is also often called as the Brewer chain. Okay. So, this is a specific name given with the which is called as a Brewer chain, which is essentially where your previous number is just also a part of the addition chain. Okay. And what we want, right, therefore, if you want to compute this a to the power of 2 to the power of n minus 2, then what we want is that this addition chain should be optimal in length. Okay. Although it is a hard problem or it is difficult problem to find out like what is the optimal chain, but there are some propositions in literature which essentially gives us efficient chains, okay, which we can use to compute this multiplicative inverse. So, taking this background or taking this addition chain into account, what we can do is this. So, if I want to now compute a to the power of 2 to the power of m minus 2, which was my inverse, then what I can do is I can define a variable which I denote as beta k. Okay. So, beta k is nothing but a to the power of 2 to the power of k minus 1. Okay. So, beta k is defined as a to the power of 2 to the power of k minus 1. So, if I want to calculate a to the power of minus 1, then therefore, as I said from Fermat's little theorem, I need to calculate a to the power of 2 to the power of m minus 2, which is nothing but the square of a to the power of 2 to the power of m minus 1 whole square. Okay. So, what is this inside the parenthesis? It is nothing but beta m minus 1 a. Okay. So, therefore, I need an efficient way to calculate beta m minus 1 and then finally, I will square to get the inverse. Okay. So, this beta m minus 1 interestingly can be computed using a nice recursive formulation. So, what I can do is I can write beta k plus j, which is like some position in the addition chain, and express them in terms of beta k and beta j. Okay. So, therefore, what I do is I try to derive beta k plus j, which is a higher beta value from the smaller beta values. Okay, and therefore, I can do it efficiently. So, why does it work? So, it is very easy to see, like beta k plus j is nothing but a to the power 2 to the power of k plus j minus 1. So, therefore, what I can write is I can for convenience I can introduce this minus 2 to the power of k and then add plus 2 to the power of k. So, basically it is the same minus 1, and then from the first two factors I take 2 to the power of k common. Okay. So, therefore, I get 2 to the power of j minus 1 into 2 to the power of k, and the other term is a to the power 2 to the power of k minus 1. So, you can note easily that this, that is a to the power 2 to the power of j minus 1 is nothing but beta j, and I have done a beta j whole to the power 2 to the power of k, whereas the other term is beta k itself. So, therefore, I have been able to express beta k plus j in terms of smaller beta j and beta k values. Okay. Interestingly, you can also observe that I can decompose this in either, like I can also write this as in the other form, like I can also write this as beta k to the power of 2 to the power of j into beta j, right. So, so which one will I choose, that may depend upon the fact that I probably would like to reduce the number of squarings which is required here, okay, because here I am doing beta j to the power 2 to the power of k. So, depending upon whether j is k small or k is small, I can write the write the form accordingly. Okay. So, if k is small, then I will write in this form. If j is small, then I will write this as beta k whole to the power of 2 to the power of j multiplied by beta j, okay, which is also correct. So, therefore, for example, let us take an example. Suppose I want to calculate for m equal to 233. Last day we saw about a Karatsuba representation for 233. So, we will take that same multiplier, apply it here. So, what we want to do is, therefore, I want to compute a to the power of minus 1, which is equal to a to the power of 2 to the power of m minus 2, where m equal to 233. So, what do I need? Therefore, I need an addition chain, right. I need an addition chain for 232, okay, which is m minus 1. So, therefore, here is an addition chain for 232. So, you can observe that it satisfies all the properties of being an addition chain, and therefore, right, what I can do is I can apply my recursive formulation, and from there I can essentially calculate the value of beta 232. Okay. If I know beta 232, then I will just do a squaring to get the corresponding multiplicative inverse of a. Okay. So, let us try to see step by step how we can calculate these beta values to arrive at beta 232 and then finally get the inverse. Okay. So, so what we do here is a corresponding tabular representation of how we can do that. So, we start with beta 1 a, which is a. So, we start with a and then we calculate beta 2 a. Okay. So, you can see that this, like if you observe the suffix here, so 1, 2, 3, 6, 7, 14, 28, 29, 58, 116 and 232. This essentially stands for your addition chain. Okay. So, these are the values which you had in the addition chain. So, now what you can do is that you can calculate beta 2 in terms of beta 1, because you can express 2 as 1 plus 1. Okay. Likewise, so therefore, if you want to calculate this, therefore, you can apply the recursive formulation. So, therefore, beta 1 plus 1 is nothing but beta 1 to the power of 2 to the power of 1 into beta 1, and therefore, you can calculate this corresponding value. Likewise, you can take any beta, for example, let us take the example of say beta 29 for example. If I want to calculate beta 29, then I can express 29 being in the addition chain as some 28 plus 1. Okay. And therefore, what I will do is I will write beta 28 whole to the power of 2 to the power of 1 into beta 1. Note, I could have also done that as beta 1 to the power of the other way round, but that would have incurred more number of squarings. Okay. So, therefore, this is a very natural thing that I will do to reduce the number of squarings. So, all in all, here we need 232 squarings. So, maybe you can count it down, and you need 10 multiplications. So, you can count, for example, 1, 2, 3, 4, 5, 6, 7, 8, 9 and 10. So, you need 10 multiplications, and if you add up the number of squarings which you are doing here, So, like for example, here you are doing a squaring, here you are doing squaring, here you are doing 3 squarings and so on, you will get 232 squarings which you are essentially doing. Now, again remember that squarings in GF2 to the power of m arithmetic is easy. Okay. So, therefore, this is a nice trade off in that sense, where you are basically optimizing the number of multiplications at the expense of squarings, which is actually quite convenient to implement in GF2 arithmetic. So, so how will I realize this by an hardware circuit? So, here is a proposal. So, of course, if I want to do a naive implementation, right, then I would have just have some squarers and then I would have repeatedly applied those squaring functions, right. But then that may not be efficient, because you can observe that in the addition chain, as you go up higher, there are some places where you are doing significantly large number of squarings, like here you are doing say 116 squarings. Okay. So, in the general case, it may happen that you are doing, so since you are doing a large number of squarings, that would, although the squaring circuit is efficiently implemented, but still if you are cascading so many squaring operations, then at the end of the day your performance will get affected. Okay. So, therefore, what you can do is you can try to trade off between hardware and the clock cycles, and rather than implementing one squarer, you can actually have a cascade of squarers. So, you can have say US number of squarers. Okay. So, US essentially is a value in the addition chain, which you have chosen by some kind of analysis, which I will try to elaborate later on. But imagine that you have got US number of squarers which you have cascaded, and then you have followed it by a multiplexer circuit. Okay. So, now suppose I want like to calculate a squaring, I want to calculate say certain number of squarings, and if the number of squarings is less than US, then what I can do is that I can just correspondingly multiplex out the output. Right. For example, if I have got say 2 squarings required, then I will pass the input here, and what I will do is I will give an appropriate control here, so that this signal, which is essentially after 2 squaring operations, gets tapped out. Okay. On the other hand, right, if the number of squarings is more than US, then you have to essentially feed this result back, okay, and you have to do say UI by US seal number of cycles. Okay. So, you have to basically keep on applying this one after the other, and you have to get the corresponding result. Okay. So, depending upon like how many number of squarings you have, you essentially have to do this configurability of, or you have to configure your hardware. Okay. You have to either give the output after one clock cycle, or you have to spend more clock cycles for getting the result. Okay. So, now what we if we can estimate the number of clock cycles required here. So, this expression shows the number of clock cycles. So, you can see that there are 3 components here. The L minus 1 term is due to L minus 1 multiplications. As I said that there will be L minus 1 multiplications which you are doing, and if you employ a combinational circuit like the Karatsuba multiplier that we saw in the last class, for every multiplication you are basically expending 1 clock cycle. So, you are doing L minus 1 clock cycles. You need 1 extra clock cycle, because this is the extra clock cycle which you need for the final squaring operation, because you have to do a final squaring at the end, and this summation gives you the number of squarings for doing all the iterations which were there in the previous table. Okay. So, you can observe that the number of squarings which you are doing, right, is UI minus UI plus 1. So, UI is one addition chain, UI plus 1 is the next addition chain. So, you are doing UI minus 1 number of squarings. Okay. So, if you go back to this table, for example, you can see that the number of squarings which you are essentially doing essentially is nothing but the summation of one is a subtraction or the difference from one UI value with the previous one. Like suppose it is 28, it is 28 and 14. So, you are doing 14 squaring operations here. Okay. So, likewise, if it is 3 and 2, you are doing 1 squaring operations here. If it is 232 and 116, here you are doing 116 squaring operations. So, that is the difference. Okay. So, therefore, right here you are so therefore, the number of squarings which you need to do is UI minus 1, and since often like it may be more than US. So, as I said that you have to divide it by US and then take the like the seal of that, and therefore, that gives you the number of clock cycles per iterations, and you have got L number of iterations. So, you vary I from 2 to L. So, that gives you the rough total number of clock cycles which you expend. Okay. So, therefore, right, once you have this, right, I mean it is fine, but at the same time you would like to optimize it. Okay. So, here is a possible optimization that you can try to sort of implement. So, so as you see that in the normal Itosuji inversion algorithm, there are a lot of squaring operations. Okay. So, so you can actually try to do an interesting comparison, that is maybe you can, what you can try is you can try to compare a squared circuit with a quad circuit. Okay. So, what is a quad circuit? A quad circuit is nothing but something which computes a to the power of 4, okay, and squared is something which computes a to the power of 2. So, here is an example which we try to work out for GF 2 to the power of 9. Okay. So, you can take an irreducible polynomial in x to the power of 9 plus so on, and then you can calculate or create this field GF 2 to the power of 9 and compute the complexities, or like the number of operations which you need to do, squarings and quads in these two for this field. So, here is like the corresponding bits like 0 to 8, because there are 9 bits which are there in GF 2 to the power of 8, and what we observe here is the circuits or the circuit complexity for calculating the squares. Okay. This one is for the quad operations. So, you can observe easily that quite intuitively the number of operations in the quad is more than the number of operations in square, because in square you are just doing power of 2, whereas in quad you are doing power of 4. But interestingly, if you look now in terms of LUTs, you will see that, and if you remember that in the last class, some of the classes we discussed that in a lookup table you essentially can fit in, like suppose if I take a lookup table with 4 inputs, you can actually fit in a Boolean function with 4 input variables. If you have got a Boolean function with 1 input variable or 2 input variable, then also that LUT gets consumed. Okay. So, therefore, right, if I want to calculate the number of lookup tables, you see that here there is no function done. So, there is no lookup table requirement, but if you have got B1 plus B5, then you have got 1 lookup table requirement. Okay. Likewise, B6 there is no lookup table requirement. For 4 B2 plus B6 you have got 1 lookup table requirement. Like this you have got 4 lookup tables which are being used. Okay. On the other hand, for the quad circuit, you will see that you still have got 1 lookup tables, but even for this value like B1 plus B3 plus B5 plus B7, where you are doing more computation, you are still using 1 lookup table. Okay. So, here at the end you are using 6 lookup tables. So, now if you compare a quad circuit with a cascade of 2 squarers, where you are doing squaring and then squaring, then you can see that there is an improvement, because here you are requiring 6 lookup tables, but here you would have required 4 into 2, that is 8 lookup tables. But in terms of delay, if you compare these two circuits, both of them have got a delay of 1 lookup table, okay, because they are consuming 1 lookup tables. Okay. So, therefore, there seems to be an opportunity for trade off, where you can try to optimize and have a better performing inversion circuit. Okay. So, what we observed is we try to kind of see it for other fields like larger fields. For example, if you see for GF 233, you will see that a squared circuit will consume say 153 lookup tables, whereas a quad will consume 233 lookup tables. But if you compare with again with 2 times 153, then you see that there is a 25% advantage. Delay wise, again both of them are same. Okay. So, therefore, naturally it tells us that like going from a squaring circuit to a quad circuit may give me an advantage, because I can utilize the lookup tables better. But the question is, you also need to generalize the Ito-Suji algorithm to work for quad circuits. Okay. So, therefore, what we do is we essentially try to look into trying to generalize this theorem, and it turns out that the first one is very straightforward. Okay. So, now here instead of doing or defining beta, we try to define alphas. Okay. So, alpha k1 is nothing but alpha to the power of 2 to the power of n k1 minus 1. Okay. So, in the previous case, what did we have? We had a to the power of 2 to the power of k1 minus 1, but now we have generalized this and put in n equal n. Okay. So, that we have generalized it to any integer n. So, likewise, if you want to make it work as a quad circuit, right, then I will make n equal to 2, okay, and that will work as a to the power of 4 to the power of k, okay, right, and essentially do power of 4 then power of 2. So, likewise, if you take alpha k2, which is a to the power of 2 to the power of n k2 minus 1, then we can see that you can actually calculate alpha k1 plus k2 in terms of alpha k1 and alpha k2. Okay. Now, this proof is very straightforward, similar to what we have already seen in the context of beta. So, I am not going to that. What about the inverse? So, once you have done this, right, and you have computed this series, then you can actually calculate a to the power of minus 1 also in a very straightforward manner. So, what you can do is, depending upon like whether n divides m minus 1. So, n, what is n? N is the parameter through which you are generalizing this quad or like higher powers of 2. Okay. So, this n is essentially here. So, therefore, when n divides m minus 1, because n may divide n minus 1, it may not divide m minus 1. If n divides m minus 1, then alpha m minus 1 by n is defined, because m minus 1 by n is then an integer. Okay. So, then if you can calculate alpha m minus 1 by n, then if you just square it, you will get A inverse. Okay. But if it is not defined, then we can write m minus 1 as n q plus r, where n, q and r are all natural numbers or integers. Then you can write this A inverse as alpha q to the power of 2 to the power of r into beta r a, and then square the entire operation. Okay. So, you can try to observe this very clearly here, that is, suppose you have got alpha m minus 1 by n. So, then alpha m minus 1 by n is nothing but, you can write this as a to the power of 2 to the power of m minus 1 by n multiplied by n. So, therefore, this n and n cancel. So, you have got alpha to the power of 2 to the power of m minus 1, which essentially is nothing but the inverse from Fermat's little theorem. Okay. When n does not divide m minus 1, then you cannot write this in this form, because m minus 1 by n is not an integer. So, there you see that alpha q, I mean essentially the right hand side of the previous equation, which is alpha q a whole to the power of 2 to the power of r into beta r, is nothing but, I can elaborate this alpha q as a to the power of 2 to the power of n q minus 1, and then raise it to the power of 2 to the power of r, multiply it with a to the power of 2 to the power of r minus 1, note that it is beta actually, not alpha. So, and then square it. So, therefore, what is this? This is nothing but alpha, or rather a to the power of 2 to the power of n q plus r, okay, minus 1, and this is squared. Okay. So, therefore, here this 2 to the power of r cancels with this minus 2 to the power of r, and therefore, you have got 2 to the power of n q plus r, and n q plus r was m minus 1. Okay. So, therefore, I can write this as a to the power of 2 to the power of m minus 1 minus 1, and which if I square, I again get A inverse. Okay. So, therefore, in both cases A inverse is correctly computed. So, what we try to do is that we just try to see if I apply quad Itosuji now, okay, and then we will see that how, or what is the amount of advantage or improvement that you get over the normal Itosuji inversion algorithm. So, if we implement this, we will see that now we will start alpha 1, we will initialize alpha 1 to say a cube, so that is a to the power of 3, and then I will try to do the addition chain, but now I do not need to go to 232, but rather I can stop at 116. Okay. So, what I will basically now do is I will try to calculate alpha 2 as alpha 1 plus 1, alpha 2 plus 1, exactly like what we have done previously, but now I have changed this to this power of 4s. Okay. So, therefore, the computation is being done fast actually, okay, is being done at a faster rate, but again as you observe that and if you compare a quad with two squarings, then the delay is same. Okay. So, therefore, right, in the initial pre-computation here, there is an amount of cost that you have to pay, because in the previous case you were just initializing with a, but now you are initializing with a cube. Okay. And remember that you do not have a squaring circuit. So, therefore, if you want to implement a power of 3, you need 3 multiplication operations. Okay. So, you need actually you need 2 clock cycles, because you have to do a into a into a. So, you need 2 clock cycles, and you also have to do a final squaring operation, which you do with a multiplication, because you do not have a squaring. Okay. So, you have got 3 extra operations which you are doing. Okay. And likewise, so and in total, right, you will see that there are 12 multiplications, because there are 9 multiplications here, and if you also accommodate this extra 3 multiplications, then you need to do 12 multiplications. Okay. Number of quad operations, you have to do 115 quad operations instead of 232, okay, which you did in the corresponding when you were operating with beta, and you also save 7 clock cycles, okay, in the process. So, therefore, right, if you just write this entire stuff, then you will see that the number of clock cycles is as follows: L plus 1 plus sigma. Now, I goes from 2 to L minus 1. In the previous case, I was running from 2 to L. So, therefore, the number of savings in terms of clock cycles is quite interesting. It is UL minus 1 divided by US minus 1. Okay. That is this extra step, and there is 1 extra clock cycle here. So, I subtract out minus 1 to accommodate that. Okay. So, therefore, right, you see that this essentially can be as high as m minus 1 by 2 for GF to the power of m. So, therefore, if you have got larger dimensions, then actually this advantage could be even more. Okay. So, with this I will briefly stop here, and I will start discussing about the corresponding hardware architecture when I am trying to realize this in the form of an architecture in my next class. Okay. Thank you.